Hi everybody, I hope you are all alright. Now, let us continue with our discussion. In the previous week, at the end of the lecture, we solved example 3 of note 3 and we found out what is the linearization for the function f of x and y equal to this around point 3 and 2. And what was our conclusion? We concluded that the linearization for this function around this specific point is this 4x minus y minus 2. And after that, in order to understand the importance of this conclusion that we've made, we did an exercise, and that exercise was this. We were supposed to calculate the value of the linearization at point 3, 0.01 to 0.01, and then again calculate the value of the actual function at that point. And at the end, we have to compare the results, right? Now, what was the result of that calculation? Now, if you remember, we did the calculations using the Symbolab. Look, the value of L at the mentioned point is 8.03. The value of F at the mentioned point is 8.03005. So if we want to compare the results, we can say that the difference between L and F is very small. Now, how small are we talking about? The difference between L and F is about 5 in 100,000, right? So the difference is negligible. What does that mean? It means that L of x and y gives us a very good estimation of the value of the function f of x and y around point 3 and 2, right? And I want to emphasize on around 3 and 2. Now, L of x and y around this point gives us approximately the same value, and it is a linear function which is much simpler and easier to work with, right? In other words, around 3 and 2, the function f of x and y behaves the same way as the function L of x and y, which is its linearization, right? So instead of working with the function f of x and y around 3 and 2, we can work with its linearization around point 3 and 2, right? So guys, the next point I want you to have in mind is that the accuracy of estimating f with its linearization at a specific point depends on our distance from that point, right? So, in the previous case, for point 301,201, you saw that the difference between F and L was 5 in 100,000, which is a very small value. Now let's see what happens if we move away from that point. Instead of 3.01, 2.01, we move to a point further away from the point of linearization. For example, 3.5, 2.5, right? 3.5, 2.5, right? If we consider this point, you see that at this point, the value of F is 9.625 and L would be equal to 9.5. You can check it for yourself, and you see that at this point, the difference between F and L is now equal to 0.125, right? So you see that the difference between F and L has increased considerably by moving from point 3.01, 2.01 to this point 3.5, 2.5, right? What is the meaning of that? The meaning is that as the distance of x and y from 3.2 increases, the accuracy of approximating F with L decreases, right? Now, guys, what if you tell me that this amount of inaccuracy is unacceptable? I don't like that amount of inaccuracy, 0.125 between F and L. Oh? So, what can be done? The, uh, the approximation has lost its accuracy. So the solution that I'm going to propose to you is to find a new linearization for F, this time around point 3.5, 2.5. If we find this new linearization around this point, we're going to reach to L of x and y, this time equal to 5.5x minus y minus 7.125. Okay, you can check it for yourself. And with this new linearization around point 3.5, 2.5, now the difference between F and L for point x and y equal to 3.5, 2.5 is equal to 0. You can check it for yourself. And guys, as an exercise, you have to do every calculation that I've done here for yourself and report it to me. Everything that I have highlighted in red and written check, you have to do the calculations, write it down, and send it to me. One in here, one here, and one here. I'm also gonna post this file into LMS so that you have access to it. Okay. So guys, now we move back to the main lecture note. Example 4 of note 3 says, find the linearization of the function f of x and y equal to 3 plus x2 over 16 plus y2 over 9 at the point minus 4, 3. Now, the solution is not complicated. In order to find the linearization, we have to determine the value of the function at the given point, the value of the derivative of the function at the given point times x minus x0 and the value of derivative of the function with respect to y at the given point times y minus y0, right? So the first one, f at minus 4 and 3, if we do the calculations, we're going to reach to 5. For round f over round x, evaluated at minus 4 and 3, if we do the calculations, we reach to minus 1 over 2. For round f over round y, evaluated at minus 4 and 3, if we do the calculations, we're going to reach to 2 over 3. So the linearization for the mentioned function at point minus 4 and 3 is 5 minus 1 over 2 times x plus 4 plus 2 over 3 times y minus 3. And if we do the simplifications on this, we're going to reach to this. Guys, here again, you can do the same exercise that we did for the previous example. You can assume a point x and y in the vicinity of point minus 4 and 3. Calculate the value of f at that point, and then calculate the value of L at that point, and see for yourself how accurate is the approximation of f with L. Now, the next subject that we're going to cover is the subject of total differentials. Now, if we want to consider the differential of a function of two variables, let us go through this process. Suppose a differentiable function f of x and y and its partial derivatives exist at the point x0, y0. Now, if we move from that point to a nearby point x0 plus delta x and y0 plus delta y, then the change in the function f would be delta f equal to f at the destination point minus f at the departure point. So it is going to be f at x0 plus delta x and y0 plus delta y minus f at x0 and y0. Now, we have found delta f. On the other hand, if we use the definition of the linearization of f, which gives you an estimation of the value of f, then the corresponding change in L is going to be delta L equal to L at the destination point minus L at the departure point. Now, that is equivalent to L at x0 plus delta x, y0 plus delta y minus L at x0, y0. And if you remember the formula we used in order to calculate the value of L, then you're going to see that this L at x0 plus delta x, y0 plus delta y minus L at x0, y0 is going to be equal to round f over round x at x0, y0 times delta x plus round f over round y at x0, y0 times delta y. Right? Now, if the point we have moved to is close enough to point x0 by 0, meaning that the delta x and delta y are very, very small values, then we use d instead of delta to show that the change in the position is very small. And we can consider df to be equal to dl. Okay, the change happening in f, we can consider it to be equal to the change happening in its approximation, right? I want to remind you that L gives you an approximation of f in the vicinity of the point x0 by 0. If we do that, we can transform this into this formula that you can see. df equal to fx dx plus fy dy. Now, df in this equation is called the total differential of f. So in summary, if we move from point x0 by 0 to a point nearby, which we call x0 plus delta x, y0 plus delta y, then the resulting change df equal to round f over round x at x0 by 0 dx plus round f over round y at x0 by 0 dy. This amount of change in f is called the total differential of f. Okay? Now, this formula, the formula for calculation of total differential, is a formula that gives you the estimation of change in the function f when its variables x and y change for a little bit. Okay? So if you have a function f of two variables x and y, and x changes a little as dx, and y changes a little as dy, then the resulting change in the function f of x and y would be df equal to this round f over round x evaluated at this point times dx plus round f over round y evaluated at this point times dy. Okay? Now, this formula has lots and lots of applications, as you're going to see through examples. One very important subject of engineering in general, which is called the sensitivity analysis, is based on a generalization of this formula for a function of multiple number of variables. We're going to see all of that very, very soon. Now, all that aside, this formula that you're seeing, this formula for total differential, you could also derive this formula when we were talking about the chain rule for multivariable functions. You remember, if f is a function of x and y, and you consider y to be dependent on x, then using the branch diagram, you could write a formula for df over dx. It would be round f over round x plus round f over round y times dy over dx. If you multiply this formula that I just mentioned by dx, you're going to reach to this formula, the formula for total differential. So this thing that you're seeing is not something very new to you. It is just that we are focusing on df and its meaning, which is the resulting change in f by changing its variables. And here we have given it a name. We've called it the total differential of f. Okay? Very good. Now, let us go through the examples. Now, example 5 says, suppose that a cylindrical can is designed to have a radius of 1 inches and a height of 5 inches, but that the radius and height are off by the amounts of dr equal to plus 3% and dh equal to minus 0.1, which is minus 10%. Then estimate the resulting absolute change in the volume of the can. This word absolute, what does it mean? It means that if the resulting change has a negative value, consider its absolute value. Okay. Now, the formula that gives you the volume of a can, which has the radius r and height h, as you all know, is equal to the area of the base times height, which is equal to v equal to pi r2 h. Now, here, the meaning of the example is that the function v, which depends on two variables r and h, has experienced a change in r, which is this big, and a change in h, which is this big. Now, the question asks, what is the resulting change in v? Now, the change that we see in v or dv, as you know by the formula for total differential, is equal to ρ v over ρ r evaluated at the starting point, which is r0 and h0 equal to 1 and 5, plus ρ over ρ h of v evaluated at the same point times dh. Okay? So we can write dv to be equal to ρ v over ρ r when v is equal to pi r2h is 2 pi rh evaluated at this point. So it is going to be 2 pi r0 h0 and the whole thing times dr. And ρ v over ρ h when v is equal to pi r2h is equal to pi r2 evaluated at r0 h0 would be pi r0 to the 2. Okay? And the whole thing times dh. Now, with r0 equal to 1 and h0 equal to 5 and dr equal to plus 0.03 and dh equal to minus 0.1, we can write dv to be equal to 2 pi times 5 times 1 times plus 0.03 plus pi times 1 to the 2 plus times minus 0.1. And that is, if you do the calculations, it is equal to 2 times 5, 10 times 0.3 means 0.3 pi minus pi, and that minus 0.1 pi, and that is equal to 0.2 pi, and 0.2 pi, by considering pi to be equal to 3.14, is 0.63 inches to the 3. Okay, this should be this should change, inch to the 3, because the when R and H are in inches, the volume is going to be in cubic inch. Okay, now the next example. Example 6 says a company manufactures circular cylindrical storage tanks. So the shape that we have here just looks just like a can, only bigger maybe. Now, part A says if the tanks are 20 feet high with a radius of 5 feet, how sensitive are the tank's volumes to small variations in height and radius? Now, in this example, I emphasize on the word sensitive. We're going to go back to it and see what it means. And part B says if the tanks are 5 feet high with a radius of 25 feet, now how sensitive are the tank's volumes to small variations in height and radius? Right, so in part A, uh, the tanks have a long height and a small radius. In part B, tanks have a small height but a very big radius. Okay? And the question asks us about the sensitivity of the volume of these tanks to variables R and H. Okay? Now, by knowing that the volume of these tanks can be calculated with the formula V equal to pi R2H, then the total differential gives the following approximation for change in volume. dV equal to rho V over rho R dr plus rho V over rho H dH, which is 2 pi RH times dr plus pi R2 times dH. Okay? Now, in part A, we see that this change in the volume at point 5 and 25, meaning dV at a point for which R is equal to 5 and H is equal to 25, is going to be equal to, if you put the proper R and H into the formula, you're going to get 250 pi times dr plus 25 pi times dH. Okay? Now, we have understood that dV at the point specified in part A is equal to this, 250 times pi times dr plus 25 pi times dH. Now, the question asks about the sensitivity of the tanker volumes to small variations in height and radius. Now, by looking at this formula, we see that a 1 unit change in R will increase V by about 250 pi units, right? A 1 unit change in R is going to increase V by this constant, 250 pi. And a 1 unit change in H is going to increase V by this coefficient, 25 pi. So you see that 1 unit increase in R is going to affect V much more than a 1 unit increase in H, right? How much more? Now, yes, the answer is 10 times, right? A 1 unit increase in R is gonna increase V by this coefficient, 250 pi. A 1 unit increase in H is gonna increase V by this coefficient, 25 pi. And this coefficient is 10 times this coefficient. So the changes in R affects V 10 times the changes in H. Okay? So the answer to the sensitivity of V to R and H is going to be that the volume of these tankers at this point, at this specific point, H25 R5, is much more sensitive to variations in R, right? And we can also say that the volume of these tankers are 10 times more sensitive to R than H. Okay? Now, this thing that we're seeing here is the basis of a very applicable concept of mathematics. And that concept is called the sensitivity analysis. Here in this example, we saw that the volume of these tanks, which was a function of two variables, radius and height, is much more sensitive to the variable radius at this specific point in part A. That can be true, that concept can be investigated for every multivariable function. And you can all understand the importance of this sensitivity analysis. In this example, you see that in part A, the volume of the tank is much more sensitive to R. So when we are building our tankers, we have to be very careful not to make a mistake in measuring and cutting the tank when it comes to the radius. Okay? A small mistake in measuring and cutting the base of the tanks is gonna cause a lot more error in the volume of the tanks. Now, let's move to part B. Now, let's exchange the values of R and H. In part B, now the tanks that we have a very small height and a very large radius, just like the storage facility for petroleum. If you have seen pictures of these storage facilities, they have a very large radius, a very big base, and rather small height. Okay? Now in part B, no, the tank in part B looks like this. The tank in part A looked like this. Now, for part B, dV evaluated at R equal to 25 and H equal to 5 is going to be 2 pi RH evaluated at 25 and 5 times dr and pi R2 evaluated at 25 and 5 times dH, which is going to be equal to 250 pi times dr plus 625 pi times dH. So you see that a 1 unit change in R will increase V by about 250 pi units, and a 1 unit change in H will change V by about 625 pi units. So now when the tank looks like this, the volume of the tank is more sensitive to changes in height than to changes in radius, right? So the designers and quality control engineers, when the tank is supposed to look like this, have to be more careful about the measurement and uh, final result for height of the tanker. Now, this figure and its caption summarizes what we learned in this example. Now, the volume of the cylinder in part A is more sensitive to small changes in R than it is to any equally small change in H. The volume of cylinder in part B is more sensitive to small changes in H than it is to small changes in R. Now, as a general rule, we can say that the functions are more sensitive to small changes in the variables that generate the largest partial derivatives, right? Because the variable that generates the larger partial derivative in the total differential formula is going to have the biggest coefficient, right? That is a very important point to keep in mind. Now, off to the next example. So, example 7 says that the volume V equal to pi R2H of a circular cylinder is to be calculated from measured values of R and H. And suppose that R is measured with an error of no more than 2% and H with an error of no more than 0.5%. Estimate the resulting possible percentage error in the calculation of V. Okay, so something rather different is asked from us in this example. We are not supposed to calculate the absolute change in V. We're not supposed to find dV. But it asks from us to calculate the percentage error in the calculation of V. What does it mean? It means that we need to find dV over V. Okay? So let's go to the solution. First, we have to interpret what this example is telling us? It tells us that R is measured with an error of no more than 2%. Now, what does that mean? It means that the absolute value of dr over r is smaller than 2%, 2 over 100, okay, which is 0.02. And h with an error of no more than half a percent. Now, the translation of this is that the absolute value of the h over h is smaller than half a percent, meaning 0.5 over 100, which is 0.005. Now, we have v is equal to pi r to h. This h is missing here. So, according to the total differential formula, we can say that dv is equal to 2 pi r h, which is rho v over rho r, times dr, plus pi r2, which is rho v over rho h, times dh. Now, here in the formula for total differential dv, we have dr and dh, but we can't use it as it is, because what the question gives us is dr over r and dh over h. So we have to change this in a way that dr over r appears here and dh over h appears here. And that is very easy to do. If we multiply the first part by r over r, we're going to get 2 pi r2h times dr over r. And if we multiply the second part by h over h, we're gonna get pi r2h times dh over h, right? Now dr over r and dh over h have appeared in the formula that we have for dv. Now look, dr over r, the formula says that it is smaller, its absolute value is smaller than 0.02, and dh over h is smaller than 0.005. So we can conclude that dv is smaller than pi r2h times 0.02 plus pi r2h times 0.005. Okay? And this, if you do the calculation, will be equal to 0.045 times pi r2. On the other hand, this pi r2h here, sorry, this is equal to pi, this times pi r2h. And on the other hand, this pi r2h here is equal to v. So the whole thing is equal to 0.045 v. And we were looking for the percentage error in the measurement of v, meaning we were looking for dv over v. So using this, dv is smaller than or equal to 0.045 v, we can write dv over v is smaller than 0.045. So the percentage error is going to be smaller than this times 100, meaning 4.5%. But one thing to pay attention to is that here, when we're doing the calculation, we considered dr over r and dh over h to only assume the positive values. but they also can assume the negative values. We can also say that dr over r is bigger than 0.02 minus 0.02, and dh over h is bigger than minus 0.005. And we can go through the same process and can conclude that dv over v is bigger than or equal to minus 0.045, this part. And from this and the other conclusion that we made, we can conclude that the absolute value of dv over v is smaller than 0.045, right? So we're not going to have an error bigger than 4.5%, and we're not going to have an error is smaller than minus 4.5%. That is the meaning of the absolute value sign that is included here. Okay, now we are ready to move to the next example, which follows the same rules but has a little bit more complications when it comes to calculations. Example 8 says, consider a closed rectangular box with a square base as shown in the accompanying figure. So it has a square base with length equal to x. If x is measured with error at most 2% and y is measured with error at most 3%, use a differential to estimate the corresponding percentage error in computing the box's A, surface area, and B, volume. Now, what is the information that this example gives us? It tells us that the absolute value of the x over x is smaller than 2%, and it also tells us that the absolute value of dy over y is smaller than 3%. Okay? Now, what is the surface area of this rectangular box? We have a square with length equal to x in the base and at the top, and all the side rectangles have length equal to x, width equal to y. So we have 2 times x2 for the top square base, for the top and bottom, and 4 times xy for the sides. So the surface area is 2x2 plus 4xy, right? Now, the total differential of s, which is a function of x and y, is going to be round s over round x times dx plus round s over round y times dy, which is 4x plus 4y times dx plus 4x times dy, right? We can conclude this formula very easily. Now, again, just like the previous case, just like the case of example 7, here we have dx, but we need dx over x. Here we have dy, but we need dy over y. So we do the multiplication by x over x here, and we do the multiplication by y over y here. Okay, here. Now, if we do that, we're going to get 4x2 plus 4xy times dx over x plus 4xy times dy over y. Now, we know that dx over x has limitations and dy over y also has limitations. So let us put that into use to find limitations for ds. Now, because dx over x can't exceed 0.02 and dy over y can't exceed 0.03, we can write that ds has to be smaller than this term times 0.02 for this, and this term times 0.03 for this. If we write that, we're going to conclude this formula. But this is a very good conclusion. The problem is we need ds over s. So we have to make s appear in the right hand side in this right hand side of this inequality, right? But how do we do that? Here in this part, 4x2 plus 4xy, because x is equal to 2x2 plus 4xy, we can write it in the form of s plus 2x2, right? If we do that, this whole thing is going to be equal to s plus 2x2 times 0.02 plus 4xy times 0.03, right? And that is equal to 0.02s plus 2x2 times 0.02 plus 4xy times 0.03. Now, some s has appeared here, some s has appeared here, but we need to make s appear in these two terms also, so that we can factorize s from all of these terms in the right hand side and get a conclusion for ds over s. Now, how do we do that? We see that here we have 2x2 and here we have 4xy. Here we have 2x2 and here we have 4xy, and their summation is equal to s, but their coefficients are not equal, so we can't factorize the coefficients to reach to a summation of these two and hence s. So we use a trick. We say that 2x2 times 0.02 is smaller than 2x2 times 0.03, right? So we can say all of this is smaller than 0.02s plus 2x2 times 0.03 plus 4xy times the rest. Now, the only difference is that here we have reached to the conclusion that we wanted. We can factorize 0.03, and 2x2 plus 4xy is going to be equal to s, and the summation of these two is going to be equal to 0.03 times s, right? Now, the summation of 0.02s and 0.03s is 0.05s, and all of this is bigger than ds. So we can say ds over s is smaller than 0.05. That is a very considerable result. And we can go through a similar process to prove that ds over s is bigger than minus 0.05. So we can draw the conclusion that the absolute value of ds over s has to be smaller than 0.05, which is 5%, right? Very good. Now, part B asked us to do the same thing for the volume of this rectangular box. The volume of this rectangular box is equal to what? It is equal to the area of the base times the height. The area of the base, which is a square with side equal to x, is x2 and the height is y, so v is equal to x2 times y. So v is equal to x2 times y. So we know that dv, using the total differential formula, is round v over round x times dx, which is 2xy times dx, plus round v over round y dy, which is x2 dy. Again, we need to make dx over x and dy over y appear. We do that by a simple multiplication and division. We're going to get 2x2y times dx over we're going to get 2x2y times dx over x plus x2y times dy over y. And here we are lucky. On the right hand side, we were looking for something that can be factorized and is equal to v. So as long as v is equal to x2 times y, we have a v here and we have a v here. We can factorize it, factorize from x to y, which is equal to v, and write that the whole thing is equal to v times 2 times dx over x plus dy over y, right? So dv over v is smaller than 2 times 0.02 plus 0.03. So dv over v is smaller than 0.07. In a similar manner, we can prove that dv over v is bigger than minus 0.07. So the absolute value of dv over v is smaller than 0.07. Sorry. The absolute value of dv over v is smaller than 0.07, which is 7%. Yes? Now, guys, after solving these examples, we're going to try to generalize the concepts that we've learned so far for a function of more than two variables. Now, if the function f depends on any number of variables, then we can also, under some circumstances, find a linearization and a total differential for it. Now, point 1 of page 11 says the linearization of f of x, y, and z, a function of three variables, at a point p0, x0, y0, z0 is the value of the function evaluated at the point plus f of x of the point times x minus x0 plus f of y of the point times y minus y0 plus f of z of the point times z minus z0. And this can be generalized to a function f of any number of variables as long as the partial derivative of f with respect to all of its variables exists at the point of investigation. Okay? Now, The second conclusion, second generalization says if the partial derivatives of f are if the second partial derivatives of f are continuous and if x, y, and z change from x0, y0, z0 by small amounts dx, dy, and dz, then the total differential df equal to fx at p0 dx plus fy at p0 dy plus fz at p0 dz gives a good approximation of the resulting change in f. That is the generalization of the idea of total differential for a function of more than two variables. In this case, three variables. But this also can be generalized to a function of n variables. Now, after this, we have to go through examples. Our time for this recording is over, and we're going to solve the remaining examples of this note in the next lecture that we're going to have. That's it for now. So, bye.